Hello everyone. In this video I'm going to explain why it is you need to make an adjustment for using this particular visualization method in the other quadratic rings and fields, that is other than the Gaussian integers and the ordinary complex numbers. Basically what it boils down to is when you go to the other imaginary quadratic rings or fields, you have a dilation first of all. With the 2 or 3 mod 4s, you have a dilation of the plane vertically, okay? And then with the 1 mod 4s, you also have a translation of the plane as well, which has to be accounted for. Now, when you take the components, say we'll take the example here of a square root of negative 2, which is a 2 mod 4 quadratic ring, okay? And say A1, A2 and B1, B2, those components don't take into account this dilation, which is expressed by the square root of negative 2. So when you take their product, you calculate their product using the components, okay? And you see the square root of negative 2 is just hanging there like I. But I is just a unit, okay? I is a unit, whatever. So it doesn't have any effect. Now, what am I talking about effect? Perhaps this isn't clear. It's when you translate all this to vectors and such. You see, if you just use these components, A1, A2, B1, B2, they're not going to include this dilation of the plane vertically. So what you have to do is you have to add that into your vectors and such. But then what ends up happening is when you take a inner product, well, that's the same in this case for the 2 or 3 mod 4s. That corresponds with the real portion of the complex product. But the wedge product, it does not include the components themselves. Well, the components themselves up here, I should say, with the elements of the ring or field, does not include the dilative factor. But this one does. It will include the dilative factor, and that will throw things off. So what you have to do for the 2 or 3 mod 4s is you have to take the dilative factor out. So in this case of the square root of negative 2, you have to divide the wedge product by the square root of 2 in order to come up with the imaginary of the product over the ring or field. And in general, you have to divide by the square root of negative d in order to take out that dilative factor to get the correct imaginary component. Now I did do a diagram here of this z of square root of negative 2 to give you an idea. It's very simple. It's just you can see the fundamental region is a rectangle instead of a square for the fundamental lattice of the Gaussian integers, the ordinary complex numbers. So basically what it is that your heights are higher. This component 5, 4 of z of square root of negative 2 doesn't take into account, I mean, it's all, 4 is multiplied by the square root of 2. Now, in order to get the distance from the axis in terms of, say, the Gaussian integers, or more importantly, what the vectors are going to think it is, you have to multiply it by the square root of 2, 1.41, whatever, and that'll give you 566, and that's the component, the imaginary component over the Gaussian integers, the regular complex numbers. I think you basically have some idea of what I'm saying here. At least I hope you do. Got to keep this under 10 minutes. Now it's a little more complicated when you deal with the 1 mod 4s. And we'll take here the simplest of them, which is of course the Einsteinian integers, where the fundamental surd is of course the principal cube root of 1. Okay, negative 1 plus I times the square root of 3 all over 2. And these are the two products, A, B of 2 Einsteinian integers and A conjugate B of 2 Einsteinian integers. Again, that paper I wrote, which I'm rewriting, explains how to get these products. And then basically you got two different things here you have to do. Is you have to, when you translate into vectors, you not only have to take into account the dilative factor, in this case the square root of 3 over 2, okay, but also you have to take into account the translation, okay, which is 1/2, okay, negative 1/2 if you will. But it's dependent upon, let's go to the second diagram, on how far up or down, whatever, that you go on the plane. It's dependent on how large it is the imaginary component is. You see the vertical dilation, that's the same idea as with the 2 or 3 mod 4s, but the horizontal translation for the real component is something new. You see, for each time you go up, if you just follow these rectangles up and so on and so forth, you see you're going by 1/2 on the real axis. You know, you can look at it here, boom, 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 boom. This is all the same real coordinate as you go diagonally this way. Just like here, that green line, that's all the same real coordinate. Okay, it's 9 up here, it's 9 down here. So you see, the corresponding, whatever, it depends on which way you're going, you have to go up to 9 or down to 6, if you will. Now, the way you calculate it is indicated up here. And it's a little bit, it can be put a little bit simpler in that basically you can, basically what it is, in order to get from 9 to 6, you have to take this imaginary component and you get divided by 1/2, okay? And then basically once you divide it by 1/2, then you have to subtract it from 9, you come up with this 6 here, okay, which is the component over the Gaussian Integers ordinary complex numbers. That would be its real component. Anyway, if you study this for a little while, maybe it'll be a little clearer than how I'm actually saying it here, but I think that gives you some idea of the picture. And basically you can figure it out arithmetically, and you see now the inner product does not correspond with this real portion, and nor does the imaginary component correspond with the wedge product. And so you can see the adjustment you have to make. You have to divide the wedge product again by, in this case, the square root of 3/2, and which is the vertical dilative factor, in order, and then boom, you get the imaginary AB again. And with the inner product corresponding to the real component of the product over the field or ring, basically the easiest thing to do is just calculate the imaginary portion first, divide that by 2, and then add it, because again, you're going this way, if you will, instead of that way. It depends on which way you're going as to whether you have to add or subtract it. The way we're going this way, we have to add it, and you can see it works out, and that turns out to be the real portion. So in general, you calculate the imaginary portion, which is the wedge product divided by the square root of -d/2, and then you calculate the imaginary portion by taking the inner product and you add the imaginary portion of the product divided by 2, and that gives you the real component of the product of two elements of the field or ring and such. I hope that clarifies it. Again, studying this picture a little bit more will probably, once you get that in your head, will make it clear, though my explanation may not help. I think the picture will probably explain it.